We're live. No, not yet. Setting up. אנשים נכנסים, מתחילים לכתוב. הנה, שניר כותב לך בהצלחה.
הצלחה לכולנו.
רגע, אני אכתוב במיטאפ גם שאנחנו מתחילים. נשלח את ה... טוב, אז אנחנו לייב ביוטיוב, שזה נחמד. אני עכשיו אכתוב בעמוד של המיטאפ, אני אשלח את הלינק ליוטיוב. אוקיי. Okay, so for Zoom webinar, for the invitation link. And this will be the stream. All right. And this can be closed for all. No, actually I'll leave this open. Okay, so we have 5 participants. ישנו 5, בעצם למה אני מדבר אנגלית. אז לכל מי שהצטרף אלינו, קודם כל ברוכים הבאים. ההרצאות יהיו באנגלית, אבל את כל המסביב אנחנו נעשה בעברית. בכל זאת אנחנו WebAssembly Israel ולא WebAssembly משהו אחר. אז נשמור על איזושהי אותנטיות.
אנטון, אתה ניטרלת את הסקרין שיירינג. אני צריך שאתה תאפשר את זה.
הנה, אוקיי, הנה, אפשרתי את זה לכל הפאנליסטס, אז אתה יכול עכשיו, אמור להיות מסוגל לעשות שיירינג, יופי. מעולה. אפילו משתמשים נראה לי באותו presentation template. האחידות. שלום לכל מי שמצטרף, טוב מאוד לראות אתכם. מי יש לנו פה? בן, אורן, סקיב, שניר, תומר. שלום לכולם. מוזמנים לכתוב לנו בצ'אט, לנו, לכולם, להגיד שלום, להציג את עצמכם גם, מכיוון שזה פעם ראשונה שאנחנו נפגשים וגם בפורמט וירטואלי, אז בואו נשתדל איכשהו להכיר. תכף גם נראה כמה אנשים אנחנו נהיה. אם אנחנו ככה נשאר בפורמט אינטימי של עד 10 אנשים, אז אפשר נגיד באיזשהו שלב, אחרי שאנחנו נסיים את השיחות, לאפשר לכולם לדבר, ואז לעשות קצת רעש.
אגב, אנחנו רוצים להשתמש בצ'אט או בשדה של שאלות ותשובות של זום?
בואו נשתמש בשאלות ותשובות, זה די נוח, אז חבר'ה, אם יש לכם שאלות, אפילו באמצע ההרצאה, אם יש לכם שאלות, תשלחו כבר ל-Q&A, ואז בסוף ההרצאה, או מתי שנוח, לשחר ולי, אנחנו נפתח את השאלות ונתייחס. ככה נגיד, אם יש לכם סתם משהו להגיד, אז תכתבו בצ'אט, בזמן ששחר מדבר אני אוכל לענות, בזמן שאני אדבר הוא יוכל לענות, והשאלות של ממש לאחרי ההרצאה, תשלחו ל-Q&A. טוב, אני עוד נותן לזה עוד דקה, אני אבדוק מה קורה בקבוצת Meetup, אולי יש שם עוד אנשים שלא יודע, איבדו את דרכם, אולי הלכו בטעות לא לזום, אולי לא מצאו את הלינק.
אני מאמין שאנחנו נהיה בפחות מחצי מכמות האנשים שנרשמו למיטאפ. זה הניסיון שלי.
זה בטוח, בדרך כלל שליש מגיע. אגב, שוב, הרישום היה יפה מאוד למיטאפ ראשון, לטכנולוגיה יחסית חדשה, וגם קבוצה חדשה. ישנו 49 רישומים.
כן, זה באמת מאוד מאוד מרשים.
רגע, תכף אני אגיד כמה אנשים נרשמו לזום, שזה לא אותו דבר. תכף אני אסתכל על זה. אוקיי, בזום יש גם 22 אנשים, שזה אומר כן, יש צפי לאולי טיפה יותר. בואו ניתן לזה, מה השעה עכשיו? עוד לא 7 אפילו. בסדר, אז אנחנו ניתן לזה עוד כמה דקות. יש אנשים שמאחרים. מה אתה אומר, שחר, שנתחיל ב7:05? פייר?
תראה, אני שוויצרי, מבחינתי השעה הנכונה היא תמיד 0:0.
טוב, אבל בכל זאת, אנחנו WebAssembly Israel. צריך לתת טיפה איזשהו פלייבור מקומי.
5 דקות נשמע לי לחלוטין לגיטימי. האמת היא שאם מישהו רוצה כן לשאול איזה שהן שאלות עכשיו, או להעלות דברים שבהמשך נוכל להתייחס אליהם, אם נראה שהם מתחברים בתוך ההרצאות, זה זמן מצוין לזה.
נכון, נכון. אם יש לכם משהו ככה שאתם רוצים להגיד, אולי אתם רוצים לשמוע, יש לכם שאלות על הקבוצה. אגב, מישהו שמרגיש שיש לו נושא לדבר, גם, כמובן, תמיד אפשר לכתוב לי במיטאפ, אני אשתף גם את האימייל שלי פה, אבל מוזמנים להגיד גם עכשיו, לא יודע, להעלות נושאים. נגיד, אתם רוצים לשאול את שאר החברים פה, אם יש לכם איזשהו נושא, והאם הם ירצו לשמוע אתכם מדברים על זה, גם בכיף.
אני מודה שהשאלה שאותי הכי מסקרנת בקשר ל-WebAssembly, אז האם אלון זכאי ישראלי?
אוקיי.
הוא ישראלי?
הוא ישראלי בהחלט, אפילו מצאתי, כשחיפשתי אותו, מצאתי איזו כתבה על הפציעה שלו איפשהו, לא זוכר איפה בדיוק זה היה, נראה לי בלבנון, כן. משהו כאילו כן, כתבות מארץ.
כבוד.
כן. אבל נראה לי שבסוף הוא כן רוצה לדבר באנגלית. יותר נוח לו, כי הוא כבר הרבה זמן בארצות הברית. אגב, חבר'ה, אם מישהו רוצה להגיד משהו, אז גם תרימו יד, אם אתם רוצים בינתיים לקשקש פה, ישנו עוד איזה 3 דקות, בכיף. אני פשוט לא רוצה לפתוח את זה לכולם, כדי שלא יהיה המון רעש, בזום זה לא עובד טוב כשכולם מדברים. יפה, יפה, התייצבות ממש יפה. שנייה, מכבה את המצלמה.
זה עלתה שאלה אנונימית, האם אנחנו מנוטרלים ומנותקים כצופים, אז התשובה היא שזה וובינר, זה לא שיחת וידאו, זה בגדול כן, כלומר במון של אנחנו מדברים ואתם מקשיבים, וכמו שאנטון אמר, אני משער שאם בהמשך נרצה אפשר לפתוח את זה כשיחה גדולה יותר, אבל כרגע זה עניין של מיקוד. כן.
כן, בדיוק, בדיוק. כדי שלא יהיה רעש בזמן שאנחנו מדברים, סתם לפעמים אנשים שוכחים לכבות את המיקרופון, כן. וואו, יפה מאוד. טוב, עוד 2 דקות, אמרנו 7:05, נעמוד במילה. רגע, אני מחזיר את המצלמה שלי. טוב, אז אני אומר שעל זה ענינו, על השאלה למה אנשים מנוטרלים.
המערכת פועלת.
אגב, חבר'ה, יש גם פולס, קצת יצרתי פה קצת שאלונים. רגע, אני צריך ממש לעשות לזה לונץ', אז שנייה, אז אני, אוקיי, הנה, אני עושה לזה לונץ' כבר עכשיו. אוקיי, אז אני עכשיו שולח שאלון, קצת להבין מי כבר משתמש, מי מתכנן להשתמש ב-WebAssembly, מי סתם מסתקרן כי זו טכנולוגיה מגניבה, ולאלה שכבר מריצים או חושבים להריץ WebAssembly, אז שואל איפה. אוקיי, מי עושה את זה בבראוזר, מי חושב על להריץ את זה על CDN נגיד, על Cloudflare שהם ידועים בזה שיש להם וורקרים שיודעים להריץ WebAssembly. הנה, יופי, אתם כבר ממלאים את השאלון. שני 12 מתוך 17 משתתפים כבר הצביעו. טוב, יופי.
אז כן, ואני אתייחס לזה.
משהו מאוד מאוד חשוב, אני אפעיל גם הקלטה. טוב, אני חושב שחר, אתה יכול להתחיל.
אוקיי, אז ערב טוב לכולם, וברוכים הבאים למפגש הראשון של קבוצת WebAssembly ישראל, מאוד מאוד מרגש. קוראים לי שחר, אני מתכנת בחברת Lightricks הירושלמית. בשנה וקצת האחרונות אני כותב מנוע רינדור לעריכת וידאו לאתר החדש שלנו שהושק לפני חודש. כדי לכתוב את המנוע הזה אנחנו אמרנו שאנחנו רוצים לכתוב אותו פעם אחת גם בפרונט-אנד, גם בבק-אנד, אז אמרנו, טוב, בואו נכתוב אותו ב-C++, נבנה אותו ל-WebAssembly ונשיק אותו לכל מקום שצריך אותו, וזו הדרך שבה אני הגעתי ל-WebAssembly. אני אוכל להרחיב על זה עוד אם יש על זה שאלות, אבל ההרצאה שלנו כרגע היא בכלליות על הסיפור של מה הצורך שהביא לקיום של WebAssembly ובאיזושהי רמה גם מה זה בעצם WebAssembly. כדי להתחיל, אני חושב sorry, I'm sorry, I forgot, this should be in English. So, I think what I said so far is less relevant, but from now on in English, sorry to the listeners at home, we probably should cut the YouTube recording to begin at the right point later on. So, in order to understand why we need WebAssembly and what niche it comes to fulfill, I want to go a bit to the ancient history of the internet, or at least not all the way back to the first days of the internet, but to the early days of widespread internet and browsers. I don't know how many of you remember this, but once upon a time, the internet looked like this. This is a static page. Some of us might not even recognize it. We haven't seen these in a long while. And the thing to notice about this page is not that it's ugly, although it is. It could have done with some more design, but all the links. Today, when you go to sites like eBay or Amazon, every one of these categories is filtered in real time in your site. But back in the early days of the 90s, each of these separate pages, these separate groups of antiques, books, computers, etc., was a separate page that was calculated on the server side, not on the front end, not in the browser itself, and then sent to the user to view. This was to no small extent because the internet was just very, very slow. And trying to do these things in the front end, both because of just transport speed of information, but also because the ability of the computers to effectively compute the new values was very limited. Today, the internet has capabilities such as this. This is real-time 3D deformation with physics and lighting, all done in a browser using the Unity engine. It is fast, it is precise, and it can run everywhere. How did we go from here to there? What were the things that were slowing us down back in the 90s and allow us today to do practically cutting edge things at native speed inside our browsers? Now, in order to understand this story, we need to know JavaScript. JavaScript is, or at least was, and I think still is, the native language of the internet. It is a language that was built for the Netscape browsers initially, but now is accepted by all browsers. It is the de facto language of the internet. This is the logic part of every website that we use. It is a very simple language to learn. It is very simple to start working in it, which meant that essentially the programmers, once upon a time, being a programmer was considered a very complex thing to do, but being a front-end programmer is today very simple because the logic is simple, the language is simple. But JavaScript was built for accessibility. JavaScript was built for generality in order to be able to run on any browser everywhere, no matter what the OS, and in order to hide from the programmer such considerations as OS and browser, etc. It was not built to be very efficient. And that meant that back in the day, even if you ignore such considerations like the speed of the computer and the speed of the internet connection, still browsers were slower. They were significantly slower than, for example, on-prem programs, native programs. And that was in no small amount because of JavaScript, which was simply a slow language. Why is JavaScript a slow language? Well, the first thing to know about JavaScript is that it is an interpreted language. It is served to the user as text. Most languages are written in text files, but when we write things like C++ or C# or Java, they're compiled either to native code, to machine instructions in the case of such languages as C or C++, or to some more efficient byte code. JavaScript, though, is received on the computer as text, and it stays as text because the user can change the language. The user can change the code. Not only that, the code can run using eval can run any string in real time. So whatever you give it, it needs to be able to handle. And that means that there cannot be an assumption that you have a finalized shape of the code that can be compiled to a more efficient format. At least that was the initial view. It is a dynamic language. That means that the coder doesn't know what are the types, or can't tell the browser what types and how to officially handle these types behind the screens. There are types. Most JavaScript engines use types behind the screens, but the code isn't built around typing, isn't built around creating a more efficient code using typing. And it is very, very abstract, which means that the code you write is very far away from the memory layout of what will actually run, from the CPU instructions that will actually run. You cannot, let's say, see it in the code, unlike, for example, C code, which is very easily translatable to the naked eye to machine code. So that was the reason that even when computers became slower, still browsers were much slower than native programs. But came around, I think, 2007, and JavaScript started to become very fast. And that was thanks to the JIT compiler, the just-in-time compiler. What happened? Essentially, browsers started using jitters that could see which code ran repeatedly, which code was entered very often. That's what we call hot code. And the browser said, okay, this code needs to be optimized. We will start learning from past runs, from past iterations on this code, and we will try to optimize it. And this gave us about a 10 times speed increase. That is, code took a 10th of the time it took before. Why was that? JavaScript tends to be slow. You need to parse the text, then you get, again, raw instructions, which are, because the code is very abstract, or not optimized in any way. And afterwards, you need to clean up whatever remains of the code, whatever remains of the objects are no longer used in garbage collection. But once you start jitting, then you can parse the text. You can say, okay, this code needs to be optimized. We will compile it. We will optimize it using some assumptions we have learned before. It can be re-optimized, again, in case we see very hot code. And I think today V8 has a third layer of optimization. So very, very hot code can be optimized a third time. But the important thing is the darker blue square, which is under execute, because once the jitter compiles and optimizes code to a certain degree, he has no longer textual code, but actual machine instructions. And executing machine instructions is very, very fast. So these illustrations aren't a single loop. These illustrations are the total time that things take, again, very broadly, as these shouldn't be taken to scale. The point of this is that once you spend the time optimizing once, twice, 3 times, you have very efficient instructions which are no longer in the form of text, and they can run very, very fast. By the way, you'll see more of these illustrations throughout my talk. Credit should go to Lynn Clark, a technical writer at Mozilla, if I remember correctly. Anyone who wants to go further in depth in what I'm talking about, check out her Twitter, check out her article on MDN. She is great and she goes into very good balance between depth and accessibility. So jitting allows us to optimize code which is expensive, which we use over and over again, into something more efficient. But it's still not perfect. Why is that? See, JavaScript is still dynamically typed. JavaScript is still an interpreted language. So even if you make assumptions about the code, nothing promises you that the assumptions will continue to be true. If you're iterating over a large array, like the illustrations show you, you might say, okay, I see that at the beginning, the first type in the array is an integer, the second is an integer, and go on and on and on, and optimize under the assumption that you're working on integers. But you need to keep checking whether you're actually working with integers or not. The compiler cannot just say, okay, the rest of the array is going to be integers, because there's nothing stopping the programmer from putting in the 10,007th place a string, or just a raw object, or whatever. Nothing protects you from that. And so the compiler still has to interject checks and tests throughout the code. There is still garbage collection. The language is garbage collected. And so the browser by itself decides at indeterminate times, times that is that the programmer doesn't know ahead of time when it will happen, that now it needs to clean up some garbage. And the programmer cannot know when it will happen, and the programmer cannot know how long will it take or how much memory needs to be cleaned up. So the programmer can't optimize for that. But given these caveats, it should be mentioned that this speed up was very, very good, and practically everyone was happy with it. That gave browsers the ability to run very complex code in real time on the browser itself and not on the server side. And that was the big break of the internet, but it wasn't good enough for everyone. So a second solution was offered, and that is asm.js. asm.js is a subset of JavaScript. It looks kind of like JavaScript. It is what you can compile from other languages into JavaScript. It is still untyped. It is it still is dynamic, but because it is compilable from native languages, it can be optimized ahead of time. That is, once you compile the code, you can see the origin code, which again is typed, has strong assumptions about things like memory layout, about CPU instructions that should be used. And so the compiler that compiles the code into asm.js has a lot more information and can optimize the code ahead of time, unlike JavaScript code, which simply doesn't give these guarantees. Essentially, it's a way to write JavaScript in a way that guarantees type consistencies and little to no garbage. I'll just demonstrate with the code we see. On the left, you have a JavaScript function, C function. On the right, you'll see the function, which is how it is in asm.js. Now, if you don't recognize the notation, notice that the I is bitwise OR with 0, which is a way of telling the JavaScript engine behind the scenes that this is an integer, to use the JavaScript integer type. And then again, you do the same thing with the returned value. Again, force it to be an integer type. And this way, the language games the JavaScript engine into being more efficient. But it's still JavaScript behind the scenes. The performance is, again, almost twice as fast than JavaScript in a bad case, nearing native speed in the best case. But it's still JavaScript behind the scenes, so it still carries the bad part, which means there is still room for improvement. And this room for improvement is WebAssembly. But before I go into WebAssembly, are there any questions? Is there anything that wasn't clear about JavaScript and asm.js? No. Okay, great. Okay, so just in order to explain what is this room for improvement, JavaScript has a limitation on types. JavaScript has abstract instructions. That means that some of the more advanced forms of optimizations which compilers today use, like memory alignment, fixed offsets into memory, or just using types which are more efficient, like more efficient for certain things like int64, int128, or SIMD, single instructions, multiple data, is not efficient. Okay, question, what is considered native speed? Native speed is how fast an efficient program will use directly on the OS. So essentially it's the same as the same as saying, if I wrote this from scratch using a native language such as C++, will this run faster in the native language, or can it run as fast in the browser? I hope that answered your question. So this niche is what WebAssembly comes to fill. Bridging the gap to close to or completely native speed using all the optimization techniques that are available to us. So what is WebAssembly? This is one way in which WebAssembly looks. We'll go into how and why it looks like this in the form later. But WebAssembly is a language with static types in which the code contains actual types. You can see here the I32, which is a 32-bit integer. It has low-level instructions. Again, unlike JavaScript, which is very abstract, WebAssembly is very concrete. Its instructions are not exactly assembly level, CPU assembly level instructions, but are very, very low level. They can be as easily translated as possible to CPU instructions. But again, since it is a universal language, which should run regardless of OS and CPU architecture, it's still not exactly one-to-one instructions. And it is pre-compiled, it is pre-optimized, it is a binary format which is sent to the browsers, sent to the consumers when it is already optimized ahead of time, which means we can put a lot of effort into optimizing it and spend a lot of time on compilation in order to reduce the runtime on the browser. Now, because the instructions are general, again, they're not concrete to the OS and to the architecture, then your WebAssembly code will again be optimized when it runs in your browser. There will be another step of compilation and optimization for the concrete from the WebAssembly to concrete machine instructions, but it is a secondary step because the assumption is there is not that much to optimize given that the code was optimized ahead of time. And of course it is, since it's binary, there's interpreting the code is very simple and very, very fast compared to textual parsing of JavaScript and asm.js. So let's go and have a brief look on what changed here. Essentially, every step of the process became faster. Parsing is faster because this is a binary format and not a textual format. Compilation and optimization is faster because the majority of the effort for compilation and optimization was done ahead of time, which means that there's also no need to re-optimize, or at least the need is significantly lesser. And then the execution time is shorter because the code is faster. Now, garbage collection at the moment is non-existent in WebAssembly. It does not support garbage collection, which means that whatever program you're writing in WebAssembly needs to manage its own memory. There is a suggestion to add garbage collection to WebAssembly. At the moment, still not happening, but who knows, maybe soon we will also have that, which might change a bit this illustration. But again, just in case it wasn't clear, the second compile and optimization step is because we're running it on a specific machine, on a specific OS, in a specific browser, which isn't known ahead of time for the for when compiling the WebAssembly. So how does it work in practice? The browser uses JavaScript almost to do everything which isn't direct HTML. Mostly at the moment today, or at least last time I checked, there was no way to call WebAssembly directly from the browser. JavaScript needs to provide a trampoline call, that is a call that tells the browser to stop running the JavaScript and start running the WebAssembly environment. The memory that WebAssembly access is essentially a JavaScript array buffer, since WebAssembly is running in a browser inside a safe sandbox. That is an environment that cannot access the rest of the computer's memory, or even the memory of other tabs in the browser. Then in order to give this memory a simulation of regular memory, which native code expects, JavaScript create behind the scene an array buffer and dedicates it to the WebAssembly as the place where memory is. Some functions pass pointers to and from this array buffer to JavaScript, and then JavaScript can pass these pointers back to the WebAssembly code. This is essentially a simulation of regular machine memory. And one of the downsides of WebAssembly is that it ran within the JavaScript event loop. I don't know how many of you know about the event loop. If there will be questions about it later, I'll be glad to go further into depth into it. But essentially, the code needs to know that it is a synchronous code that is running inside a asynchronous environment, and so it needs to know when to return. It needs to know to yield control back to JavaScript in order to let the JavaScript event loop continue running. All of these things incur still a small overhead. So all of these things mean that at the moment, WebAssembly in your browser, even when you remove whatever overhead the browser itself imposes, still it's not exactly as fast as running directly on the OS. But this overhead is relative to JavaScript and asm.js very small, And so not exactly as fast, but we're really nearing the top of the speed that we can achieve inside a browser sandbox. And I just got a correction from a friend that says that WebAssembly in Chrome, that Chrome can directly call WebAssembly. So the first part about trampoline calls is very often true, but not necessarily true. Now, the last problem we have in WebAssembly is that there is no direct access to the sites and the browser's DOM, which means that at the moment, in order to change things in the DOM, document object model, essentially what defines how the site looks and what the HTML parts that it contains, JavaScript needs to make callbacks into WebAssembly, WebAssembly needs to have callbacks into JavaScript in order to modify the DOM. Again, there is a proposal to change that and allow WebAssembly to directly access the DOM, but at the moment, if you need to use that, there's still small overhead there. So how does WebAssembly look? The left representation is how it looks in what is called S expression, scheme expression, because it's a functional representation that follows very closely to the standard of the scheme language. You can notice all the parentheses, which define scope of functions. It is easier to read once you're used to it, but not the most readable format. The right side, the middle box, sorry, is another representation, which is more similar to how regular assembly looks. But again, I'll remind you that we said that WebAssembly is a binary format. Whether you have the left representation or the middle representation, the way the code is actually written is in bytes. We simply have textual, and we have IDEs which can read these bytes and translate them into differently formatted styles. But the rightmost box, WASM binary encoding, is what is sent to the browser. It is concise, it is small, and it allows us to quickly send our code to the browser. Now, I know that most of us don't want to write an assembly. We certainly don't want to write bytecode, but we also don't want to write very low-level code, which is not the most convenient thing. There is a reason that most of us don't write as assembly. So the good news is that you can compile WebAssembly from a lot of platforms. There are over 30 languages which have some compilation support to WebAssembly, including JavaScript itself, which can be compiled into WebAssembly. I'm not sure what scenario is that used, but great. I would say the chief platform for compilation is the Emscripten platform. It's an LLVM backend, which essentially takes the LLVM project, which, in case you know, is a project that allows universal translation of one language into another. It is, I think, most famously used for Clang compiler and the new Rust compiler, but it's a project that allows you to change both what language can be interpreted and also into which language it can be interpreted. So Emscripten is a project with a backend that allows LLVM to create WASM code. It also has a lot of built-in optimization, a lot of built-in support for such language constructs which are not strictly supported by WebAssembly. For example, WebGL, the web graphics language, is not compatible with WebAssembly at the moment. But if you write OpenGL code in C, C++, etc., then it will mscript and will know to wrap this code in WebAssembly code, which will call JavaScript, which will use WebGL behind the scenes. So like in my scenario, I write OpenGL code to run on the server side and compile it. So behind the scenes, it runs WebGL code in the front-end side. There's also the assembly script, which is a language very, very close to TypeScript, but the same way that TypeScript compiles into JavaScript, assembly script compiles into WebAssembly. Rust has a built-in compile target for WebAssembly. So people who try out Rust, first of all, I envy you. I want to try it out. I want to have the time to fully try it out. But be happy to know that you have language and compiler support for that to compile into WebAssembly. And there are more projects. There is, for example, the WASM project, which allows independent compilation into WebAssembly. So whatever language you work in, or at least whatever large common language you work in, there's a very good chance that you have some compiler support for it to WebAssembly. Now, so far I talked only about WebAssembly in the browser, but one of the things that WebAssembly is designed to be, since again it's designed to run in browsers, regardless of which browser it is supposed to run on, which OS and which architecture it is supposed to run on, then people have reached the rather obvious conclusion that don't need a browser in order to run WebAssembly. The name might be confusing because WebAssembly is not only for the web. WebAssembly can be run on any target which can read the WebAssembly instructions and translate them into specific machine instructions. And a lot of people talk about using WebAssembly everywhere, everywhere. And some people say, okay, maybe WebAssembly is the future. Whatever language we will write in, everything will be compiled into WebAssembly, and it will be much easier to just have a lot of targets that know how to run WebAssembly instead of compiling everything into different targets. Is WebAssembly the future? In my opinion, no. I think that WebAssembly is not that much different from JavaScript, Python, Java, C#, etc. Other standards and languages which allow you to run your code practically everywhere. I don't think there's a distinct difference there, but I might be wrong. We might find that WebAssembly being very low level and very concise in a format might actually make it a universal standard. I guess we'll see. But that's for the future. I hope that was clear. I hope you now understand how the internet, how browsers became that much faster, and what niche WebAssembly comes to fill. If there are any more questions, we'll wait, I think, a minute or two. And if not, I guess we'll go into the second talk of the evening.
Well, thank you, Shachar. I think this is wonderful. Very, very clear. You know, for me, it was the right amount of detail, like diving deep enough to understand what this is about, you know, not staying on the surface only, but on the other hand, and you know, this was detailed enough. So I did learn new stuff from this, even though I started looking at WebAssembly something like a year and a half ago. I still learned a couple of new things from your talk. So that was great for me.
Thank you.
And I'll switch to Hebrew for a bit. חברים, שאלות? לא יכול להיות שאין לכם בכלל שאלות. כל שאלה אפילו הכי מטומטמת היא גם לגמרי בסדר. אוקיי. שחר, אני לא זוכר, אתה הזכרת מה השימוש של WebAssembly בעבודה שלך, אם יש שימוש, זאת אומרת, מה פחות או יותר מה אתם עושים עם זה?
כן, אז אנחנו עובדים, אני אכתוב עכשיו בצ'אט את שם האתר, מי שרוצה מוזמן לנסות אותו. אנחנו השקנו עכשיו אתר חדש שמאפשר לבצע עריכת וידאו בזמן אמת בדפדפן. הקוד שעורך את הוידאו הקוד שמרנדר את הוידאו רץ בדפדפן, אותו הקוד בדיוק רץ בבקאנד שלנו כאשר אנחנו שומרים את הקבצים, שומרים ממש לקבצי וידאו. אז זה אפשר לנו לכתוב קוד ב-C++ פעם אחת ולקמפל אותו לכמה מטרות. ויש לנו שתי שאלות. אז השימוש העיקרי, מה השימוש העיקרי ל-WebAssembly? אני חושב שהתשובה הנכונה היא הכל. השימוש הבולט ביותר הוא אם אתה רוצה להריץ קוד מהיר ויעיל בדפדפן, או אם יש לך קוד שכבר כתוב בשפה שלא ניתן להריץ בדפדפן, ואתה רוצה לקמפל אותו לדפדפן. אלה השימושים הראשוניים והבולטים ביותר, אבל אלה ממש לא השימושים הבלעדיים, והשפה עוצבה להיות גמישה מספיק, כדי שבאמת התשובה תהיה, כי אתה רוצה להריץ את הקוד שלך איפשהו כלשהו. זה הייתי אומר השימוש האולטימטיבי של WebAssembly.
כן, בעצם הוא נוצר במוזילה כדי להריץ קוד בבראוזר, אבל אז הם גילו שהם המציאו פה איזשהו פורמט שאפשר למעשה לעשות איתו הרבה יותר דברים, ויש לזה פוטנציאל. אחד השימושים גם שידועים עכשיו זה ל-Cloudflare, ה-CDN, יש להם עכשיו וורקרים שמאפשרים להריץ WebAssembly ממש על ה-edge, ממש ב-CDN עצמו.
שאלה שנייה של בן חורין, אני חושב. האם הקוד המקומפל זהה בכל פלטפורמה? התשובה היא כן. זו בדיוק המהות של WebAssembly. אתה מקמפל פעם אחת ל-WebAssembly, שולח את זה לכל מקום שאתה רוצה, ובמקום הזה, מה שמריץ את ה-WebAssembly, מבצע שלב שני של קימפול לפלטפורמה הספציפית ולטרגט הזה, אבל הבייטים שנשלחו הם אוניברסליים. אז יש קימפול קטן יותר, כמו שה-JVM מקמפל את הבייט קוד של Java, אבל הקוד עצמו שנשלח, הבינארי שנשלח, הבינארי שאתה המתכנת קימפל, אוניברסלי. הטרגט והפלטפורם שלך זה WebAssembly. לא משנה איזה מעבד, לא משנה איזו מערכת הפעלה. אורן שואל, מה ההבדל של היכולות של הקוד שלכם בין מה שרץ בשרת ומה שאתם מריצים בדפדפן? מבחינת יכולות גרידה, אם לא סופרים דברים, אוקיי, יש דברים שאיטיים יותר מדי לדפדפן, כמו לבצע אנקודינג לוידאו. זה מי שלא נכנס לתהליך הזה, אשריו וטוב לו, זה מסובך, זה כבד, זה כאב ראש לא נורמלי. אנחנו שוקלים מתישהו בעתיד להכניס את זה כניסוי, אבל כרגע אמרנו שאנחנו לא יכולים לסמוך על זה שלמשתמשים שלנו יש יכולות חזקות מספיק בדפדפן כדי להבטיח שנעשה אנקודינג בזמן אמת בדפדפן, אז הקוד בצד השרת מבצע אנקודינג של וידאו. מבחינת היכולות הגרפיות, הקוד זהה לחלוטין, עד כדי פלאגים של פה אנחנו משתמשים בגרסה אחת של OpenGLES, ופה אנחנו משתמשים בגרסה אחרת, אבל אלה הבדלים מינוריים. מבחינת היכולות, מה שהקוד עושה, אותו הדבר עד כדי video encoding. Can we compile Python code to WebAssembly? אז במצגת יש קישור, אני די בטוח שכן.
כן, כן, יש.
מצוין. אפשר לקמפל קוד ל-WebAssembly. WebAssembly זה שאלה נוספת. WebAssembly זה לא רק לדפדפן. Any known use cases? ובכן, זה נשמע לי סגווי מצוין לאנטון, שבאמת עובד עם WebAssembly, לא בדפדפן.
נכון, נכון.
בכבוד.
עכשיו, אני רואה שיש עוד שאלה בצ'אט. שואלים אם יש ל-WebAssembly ספריות.
כרגע, ככל שידוע לי, WebAssembly לא תומך בספריות, אבל צריך לזכור שספריות זה ככלל קוד לפני קימפול. אתה בהחלט יכול לקבל ספרייה של C, ספרייה של C++, ולקמפל אותה ביחד עם הקוד שלך ל-WebAssembly. מה שאין לך כרגע זה שווה ערך, ככל שידוע לי, זה שווה ערך ל-Dynamic Linker. כלומר, ספרייה שמקומפלת מראש ואתה מתחבר אליה לאחר מכן מהקוד שלך. אני חושב שיש הצעה לעשות את זה, אני לא ב100% בטוח, מכיוון שזה פותח בעיות אבטחה לא קטנות. והקישור בצ'אט לא נראה, אני שלחתי אותו בצ'אט, אני שולח אותו שוב, אבל מי שרוצה זה פשוט boosted, boosted.lightricks, lightricks.com. אני שלחתי, אתה צודק, שלחתי לכל הפאנליסטים. תודה רבה, אורן. אני שמח שיש מישהו שמבין בזום יותר ממני בקהל. הנה. עכשיו כולם רואים?
כן, יפה. אני לא שמתי לב, כי אני רואה את זה כפאנליסט. אוקיי. מעולה. חבר'ה, תודה על כל השאלות, ושחר, שוב תודה. מחיאות כפיים, היה מעולה, ונעבור לטוק שלי. יאללה, אני אחבר לך את המיקרופון, או שתחבר אתה בעצמך. ואני אעלה את המצגת שלי, רגע, שאני כמובן שלא הכנתי אותה, הייתי כל כך עסוק בשיחה שלנו. אוקיי, ופה סגרתי אותה. אוקיי, הנה המצגת. So I'm loading up my presentation, and while that happens, okay, here it is. And it's time for me to share my screen. Sharing my screen, share. Yeah, you should be seeing my screen right now. Okay. Okay, so I hope everybody hears me okay. If you have any issues, please do write in the chat. Okay. And yeah, right. Okay. So for those of you who don't know me, and that will probably be majority of you, my name is Anton, or as folks call me, Ant Weiss. I've been in the industry for the last 20 years. I started with the development, went through an array of integration, management, even product roles. About 9 years ago, I started dealing with, eventually got called DevOps in most organizations today. And well, all this definitely makes me an expert in one thing, and that's imposter syndrome. And I continue digging that hole by blogging and speaking on all kinds of issues that I pretend to understand. And that's why today I'm going to be telling you about how to extend the Envoy network proxy with WebAssembly modules written in Rust. Now, WebAssembly we already talked about, Rust got mentioned, and still if this sentence doesn't make any sense, don't worry, it will all become clearer once we're through the talk. So, here's our mighty trio, Envoy, WebAssembly, and Rust, right? So here they are. They're the heroes of the bleeding edge cloud native tech, and we can start the saga. And we'll start with Envoy. She's a very nice, young, fresh network proxy, born about 4 years ago at Twitter. No, sorry, at Lyft, the ride-sharing company, but it is based on its creator's, Matt Klein, previous experience of running a gazillion of microservices at Twitter. Now, evidently, running a lot of microservices is hard, and that's mainly because all of the network connections between those services can become a serious bottleneck if not managed correctly and efficiently. And that's exactly where Envoy's superpowers shine. It's written in modern C++, so it's very performant, and it takes care of L3, L4, and L7 connections. And it quickly became widely popular. Significant drivers of its adoption being its high configurability and extensibility, right? So all this led to Envoy becoming the base component in a buzzing hot cloud native tech that a lot of folks seem to be talking about lately. And by that, I mean, who knows what I mean? If you know what I mean, you're welcome to write in the chat. So we'll see if you guessed it right. And that reminds me, by the way, that there is a poll for my talk that I wanted to run. So if you guessed, and we'll see in a moment if you guessed right, because I'm talking about service meshes, of course, right? So let me run the poll for a second. Where's the poll? Okay, we'll stop sharing this. And we'll go to poll number 2. I'm launching it right now. And we'll get this out of my way. And yeah, we'll continue. So service meshes, right? Envoy has become the base component in the main leading service mesh implementations, such as the AWS App Mesh, HashiCorp's Console Connect, and VMware's NSX, and Kong's Kuma. And I'm sure some of you have been waiting for this one, Istio, of course. So Envoy is the network proxy in those service meshes. We won't be talking about what service meshes are. If you want to hear me talk about service meshes, let me know. We can have another meetup for that. But what I wanted to say is that Envoy is widely popular, and popularity, as we all know, is a double-edged sword, right? So on one hand, it allows the project to grow faster. It attracts the community. Isn't that what we all want? But on the other hand, the more users are out there for our project, the more functionality we'll find ourselves needing to implement. And we all have different needs, right? So there are different feature requirements. And at a certain point, we need to be able to extend functionality more and more. And that's how Envoy's extensibility model, the existing extensibility model for Envoy, became limited, right? It hit its limits. In fact, up until now, if somebody wanted, I said that Envoy is extensible, so it is extensible. Up until now, if somebody wanted to extend Envoy's functionality, they had 3 options. So the first option would be to write the extension in C++ itself and statically link it into the Envoy binary. Well, this is suboptimal. First of all, because Envoy, it's a C++ build, a very heavy one. So it takes a long time to build. And then think that in a service mesh, you could have dozens or even hundreds of network proxies inside your mesh. So think that you'll have to rebuild the Envoy proxy binary and redeploy it dozens or hundreds of times for each extension change or addition. Doesn't work. So another option would be to extend Envoy's functionality out of process. So sending the traffic from Envoy to another process, do something with the traffic there, and then go back to Envoy. That's what Istio originally did, but that also doesn't scale because you effectively add another network hop, and that just cancels out all of Envoy's performance gains. And there was a third option also that would be extending Envoy with Lua scripting, a bit like it's done for Nginx and OpenResty, but that currently only supports HTTP traffic. And quite frankly, how many folks out there like writing Lua, right? So a better, new, more cooler extensibility model was needed, and it didn't take too long to arrive, because now we can extend Envoy's functionality, and you guessed right, writing WebAssembly modules. So I won't be speaking too long about WebAssembly. Shachar just gave a great talk about what it is and what it does. But basically, the great thing about WebAssembly is that it's a universally binary code format. So once we have in our project an ABI, which is an application binary interface, which supports running WebAssembly, we can actually integrate WebAssembly modules in our application. So it becomes a great format for extending applications and for plugging frameworks in such languages that before that didn't have a very good framework for plugging and extensibility, such as C++, for example, right? Okay, so we can now run WebAssembly in Envoy. Now, WebAssembly, another great feature of WebAssembly that we also talked about is that it allows you to actually write your module in almost any language. We have compilation targets for a lot of languages with mainstream support for C++, AssemblyScript, and Rust, right? Rust was also mentioned by Shachar, and that brings us to our third hero, the third part of our trio. Rust is a relatively young language, also invented at Mozilla, just as WebAssembly itself. And it's known for its very efficient and safe memory model, right? It's impressive expressiveness. Can somebody say impressive expressiveness? I guess yes. So it's very performant. It gives us native performance, right? And it has great support for functional programming and meta programming. And the main factor is its ultimate lovability. Seriously, according to the Stack Overflow survey, Rust has been the language most loved by developers for the 4 last consecutive years. And that, if you ask me, is a very important feature for any engineering tool. If engineers love working with the tool, that means that tool is good. And that's a tool that you'll want to adopt, right? So we have Envoy. We can write WebAssembly modules for Envoy, and we can do that in Rust. So when our 3 heroes get together, no villain will be unslain. And the next part of my talk will actually be live coding. Am I crazy? I don't know. We'll see in a moment. And the plan, here's the plan for making our 3 heroes play together. We'll have a build stage at which we'll create a Rust WebAssembly model for Envoy. Then at deploy stage, we'll load the module we've just created into an Envoy running in a Docker container. And then to test that our module actually does the work that we do, we'll proxy the traffic through that Envoy running our WebAssembly module to an instance of HashiCorp HTTP echo, which is basically just a very small web server that echoes at us whatever we tell it to if it receives a request. right? So at the build stage, what we'll do, we'll create that WebAssembly module. It will be based on a crate, which is Rust's lingo for library. There are crates, libraries available at Rust's public package registry called crates.io. So crate, yeah, it's not a library, it's a package. That would be a more correct definition. Inside our code, we'll implement the base context trait. A context in Envoy is that traffic that we're processing. Over that, we'll implement an HTTP context trait, which takes care of HTTP traffic. And for that implementation, what we'll do is we'll be filtering HTTP headers to create a pandemic authorizer. That authorizer will only allow requests when they have a header called temperature, and when that header has value below 37.0. Sounds familiar? I'm sure it does. So without further ado, let's start coding. Okay, so you should be now seeing my screen. I'll enlarge. By the way, any questions up until now? Let me see. So I don't see anything in the chat, nothing in Q&A. So you're probably all are asleep or impatiently waiting for me to start coding. Okay, so I'll clear it up a little bit. Okay, the first thing we need to do is create our library. So for that, we'll be using Rust's wonderful package manager and build automation tool called Cargo. Okay, we'll say Cargo, we want a new library, and we'll be calling that pandemic auth. Okay. And Cargo creates a new library. So we'll go to the directory that Cargo created and fire up a new Visual Studio Code instance in that. Okay. So here's a new Rust project right here. It has a source folder inside which there's one source file called lib.rs and the very important cargo.toml file, which defines for Cargo how to build our project. And the first thing we'll need to do is to depend on proxy WASM crate that will allow us to implement the traits needed for our WebAssembly model to be able to run inside Envoy and perform the functionality that we needed to perform. So we'll say we're depending on a crate called proxy WASM. And the version that's publicly available right now is 0.1.0. Okay, we'll save that. And we can start coding. So this Cargo already created a small dummy test for us. We'll just let that go. Tests are important, but not for our use case right now. And we'll say that we want to use from proxy WASM. We want to, first of all, import the types. We don't really need all the types, but for simplicity, I'll just import all of them. And then I'll use proxy WASM traits. Traits, if you code in Rust, you know what that is. If you don't code in Rust, you'll know that you should know that traits are Rust's mechanism for extensibility. Okay, a little bit like inheritance in other languages. So once we have that, we can start creating our context, our filter. So the first thing we need to do is create an object for that. That would be a struct called pandemic authorizer. Okay, and that struct only needs to have one field, and that will be the context ID. And that field will be U32. Right, once we have our struct, we need to start implementing the traits for it. So we'll go and say impl, we'll need to implement, as we said, the root context, okay, for our pandemic authorizer. And for that, we don't need to do anything for that implementation. We just need to make sure that we implement that, but we are not processing anything lower than the HTTP level. So our actual functionality will be inside the implementation for HTTP context. Okay, so we'll do implement HTTP context for pandemic authorizer. For this implementation, we'll need to create a function. So our function will be on HTTP request headers, and that will receive a mutable reference to the context itself. And it also receives the size of the headers. We won't be using that, so we'll just replace that with an underscore. Inside the function, of course, needs to return something. What it does return is an enum called action, which tells Envoy what to do after the processing has completed. So inside that, we'll use Rust's match clause on the result of self get HTTP request header. And we'll be looking for a header. If you remember our build stage, we'll be looking for a header called temperature. Okay, so once we found that header, we'll say if we found the header, if we received something, okay, and that something is T, and if that T, when we parse it into a float, returns something, it is okay, that parsing. And also, not only that it returns something, we also can see that when we've parsed it, and unwrapped the result of that parsing, the result that we received is smaller than 37.0. Yeah, that's the temperature that's allowed by our authorizer. In that case, what we tell our filter to do is to, first of all, resume the HTTP request. So we send the traffic further to wherever it was destined to, right? This is all done in the proxy. So the traffic is proxy. So we say it's okay to proxy the traffic further. And we tell Envoy that it can now continue listening and processing for other requests, right? Okay. Now this is when we do receive something and it satisfies our requirements. What happens when it doesn't? This is the other hand of our match clause. And that's where we'll say, okay, we didn't receive the temperature, or the temperature was too high. So we'll send an HTTP response, and that won't be a nice response. We'll send 403, of course. And we'll send some headers. It will be a vector of headers. We'll actually send just one header. We don't have to, but it will be nice too. So we'll say this request was stopped by, and we'll send our context ID for that. So we'll say self context ID. We'll need to convert that to string in order for it to be an OK field for a header. And we need parentheses around this. And finally, the body of our response will be an option, which will have a binary string, a byte string inside that, which will say temperature is too high or not measured, right? So that's why we didn't let that through. And with that, our response is sent, and we can tell Envoy that we should now pause and wait for the next request. Right, so that's our implementation, that's our authorizer. Now, the only thing is that's now missing, we have the filter, we now need to initialize that. So another additional thing that we'll need to add here is public function that will be called start. Okay, and inside that function, we will be calling proxy WASM set HTTP context, and that receives a callback. Sorry. Okay, that callback receives the context ID and another variable that we'll currently ignore, and it returns a box, which is what we use in Rust when we don't know what exactly type we're going to be returned. So this just reserves the place in memory. As we said, Rust has a very efficient memory management model, so it has to know exactly how much place in memory everything needs. So we say we're just returning a box. Inside that box, we'll have a dynamic object that implements the HTTP context trait, right? And what will that callback do? Well, inside it, we'll just call box new to create that box. And inside the box, we'll put an instance of our pandemic authorizer that's initialized with the context ID that we received from our caller, right? Okay, and one more thing missing. This will be a function that will be called from the external C++ code. So we need to add Rust annotation that says no mangle. So Rust compiler usually mangles, it changes the symbols inside the Rust libraries. We say we don't want to mangle this one, so it can be found from external code. Okay, with that, our code is ready to be compiled. And I go back to our console and do cargo. And we will be using cargo's nightly release because this is all bleeding tech, and we'll be compiling our code for the target WASM32 unknown in release mode. Let's see if it compiles. So yeah, it definitely looks like it does, but my computer is terribly slow with Zoom and everything running in it. Ooh, cannot find context ID in this. Okay, yeah, right. I have a typo. So with that fixed, am I okay? Oh, okay, and here, 2 typos. That should fix it. Right, so we've built it. Let's see if we have the WebAssembly model built. So we'll go to target and right here, and inside the WASM32 unknown, we see that the library got built, but we don't have a WebAssembly model because a WebAssembly model should have a .wasm extension. So for that to happen, we need to go back to our cargo toml and add a section here that will be telling cargo what kind of library to build. So what we'll say here is our library will be called pandemic auth, because that's what my Envoy will be expecting. And the crate type, which is important, will be this cdylib, which is a dynamic library mounted from C++ in our case. Right, let's rebuild. And if we go back here, we'll see that here is our WebAssembly module, right? So we have our binary format right here. Now, the only thing we are left to do is to deploy and test. For that, I have files prepared beforehand. So what did I just bring in? What I have here is this. Well, here's this folder called Envoy. What it has inside it is a Docker file, which builds, it actually doesn't build, it uses the version of Envoy which comes from the Istio project, because that version of Envoy has the richest WebAssembly support for that specific proxy WebAssembly crate that we were using as our dependency, right? And it runs Envoy using the configuration file etc envoy.yaml, and that file sits right here next to our Docker file, and we can see that in the filter chain, which defines how the traffic is filtered in the proxy, there is a filter called Envoy filters http.wasm. It's called pandemic auth. The runtime for it is V8, and it loads the WebAssembly model from a local file called etc pandemic.auth.wasm. By the way, the code can also be loaded from an external URL, and I'll say a few words about that in the end of the talk. Right. And finally, so this is the Docker file. And finally, right here, I have a docker compose.yaml, which says that we're running our proxy. It's based on this Docker file that we just saw. And it mounts the configuration file envoy.yaml and also our freshly built pandemic auth.wasm as the WebAssembly filter for Envoy inside the Envoy container. We can see that the container will be exposing port 80, and that will be mapped to our port 18,000. And we'll also see that we're proxying the traffic to a web service based on HashiCorp HTTP echo, which when it receives a request will be saying welcome to WebAssembly land, right? Okay, so without further ado, let's deploy and test. So what we need to do is do docker compose up. Okay, it looks like our proxy is running, and I'll go to another shell and I'll do curl. Well, the first thing we'll do is we see how it fails. So we'll send something like 37.2. So this is the header called temperature. I hope you can see my screen. I'll enlarge. Right, and we're sending this, as I said, Envoy is listening on port 18,000. So I'm sending this to my host on 18,000. And I'm receiving temperature is too high or not measured. And right here, I can see that this is what our module outputs. So it says, I'm sending back status 403, and this is stopped by context, which has the ID of 2, right? Okay, wonderful. And now we go back and we send the request with the temperature that is okay, a healthy request. Let's say 36.6, shall we? And we're receiving welcome to WASM LAN, which is exactly what we expected to receive when the request is healthy. Our pandemic authorizer allows it to go through, and everything looks wonderful. Great. So let's stop this here. My computer is loaded as it is. Okay, let's sum it up, folks. So Envoy is a great network proxy that is now proxying the biggest part of the cloud native world. Another option for proxying in cloud native is, of course, Linkerd, which is itself written in Rust, but doesn't have WebAssembly integration. WebAssembly is a scalable dynamic extension mechanism that can be used on Envoy and potentially in many other processes and systems. And writing WebAssembly models in Rust is fun because writing Rust is fun, and we can compile Rust into WebAssembly. So another point that I touched upon, if you run Envoy with console, you can take a look at this project called Image Hub, which comes from Layer 5 IO, which is a community dedicated to the research and development of service mesh technology that I'm a part of. It basically allows you to store WebAssembly modules in this image hub and load them into Envoy. As I said, Envoy can load WebAssembly modules from external URLs and not only from local files. And that's it, folks. I'll be happy to take your questions. Yeah, I'll unshare my screen. So we're still here, right?
I have one question, actually.
Sure.
What did Envoy use before WebAssembly? What's the lesser alternative?
Yeah, I mentioned this. So before that, if you wanted to extend, you needed to just, there was a format in which you could write it in C++, just create a library in C++ and just statically link it into the Envoy code.
Yeah, that was statically linked, though. So you couldn't deploy plugins on the spot.
You couldn't. The only other option was extending it with Lua. So they had a mechanism. So there was a plugin that allowed you to write Lua code, and then it was sent to that Lua code. And well, that works kind of okay, but it only allows you to take care of HTTP headers, which is okay for this use case that I just showed, but not for other cases, because Envoy is great at proxying also at lower levels. And well, again, Rust is much nicer than Lua, and you don't have to write in Rust only. You can also compile C++ and assembly script, so you have more options with WebAssembly. And it's safer, of course, and more performant. So what's not to like? Any questions regarding Rust? I'm not a Rust expert, but I find it very lovable. Regarding Envoy, regarding WebAssembly. Okay, everybody's tired, I suppose. I'm tired myself. Well, would anybody, oh, okay, here's a question. Who's developing the SDK for Rust? You mean the crate, right? I suppose you mean the proxy WASM. So the library, the package. It's being developed by the Envoy team, specifically the folks at Istio. It's all a little bit intermixed, right? So Envoy was originally a project developed at Lyft by Matt Klein, but now Google is so interested in pushing Istio forward because it's their project that they actually took over most of the development of Envoy itself. So it's pretty hard to understand who those people work for, right? Somebody here, Tomer, says it's Solo.io. So Solo.io is a great startup that's very involved with the service mesh technology and specifically with WebAssembly modules for Envoy. They've launched their project called WebAssembly Hub some time ago that allows the same thing that Image Hub from Layer 5 allows to do, which is loading WebAssembly modules into Envoys running in Istio in your Kubernetes cluster. Somebody asked, what's a service mesh? Well, that requires a separate answer. I suggest you Google this because, well, basically a service mesh is something when you have a microservice system with a lot of services talking to one another over the network, that becomes very hard to manage. So in order to simplify and make the management of these interactions to abstract away the management of these interactions, there is this kind of technology called service mesh, which is basically a network of very lightweight proxies that proxy all of this traffic and can be centrally managed, and you can define different rules on the network level and not on the service level. That's, hope this explains it in a very few sentences. So back to what Tomer says is that is Solo.io, are they developing the SDK for us? No, I don't think. I think the folks who I saw on the committers for Proxy WASM, by the way, you can find the project is freely available on GitHub, so you can contact its developers. You can start contributing to it. It's an open source project. I think there are folks who work at Google, but don't rely on me. Check that. I don't think it matters all that much because it's an open source project. Okay, so I've answered this one, and I've answered this one, and let's say I answered what a service mesh is. I can actually send a link to, yeah, right. I'll send a link to my talk. I think I'll post it in the Meetup group or maybe right here. Yeah, just give me a second. We'll exit this one. So there's a talk I gave on the evolution of service meshes at Cloud Native Days Israel called WTF, do we need a service mesh? It's on YouTube. Okay, right here. So I'll send that to the chat. And we have another question. It's actually, what is a service mesh? So we've answered this one too. Okay, and what's with our poll? We have another poll. I think, all of you answered. Great. Okay, wonderful. Okay, I'll end the poll. I'll share the results with you so you can see the results of this one. So there are some other folks beside me. There are 3 participants who run service mesh in production. Now, this is where, first of all, thanks again to Shachar. Thanks to all of you for coming, for participating. Great questions. Don't miss our next meetup with Alon Zakai, which will be exciting to say the least. This is the guy who wrote the Inscripton that co-created the Inscripton, and his talk is called the vision of a universal binary. So he'll be covering some of what Shachar touched upon at the end of his talk. And as I said, we're looking for more speakers. We want to hear your experience with WebAssembly, even if you're just, diving in, or if you've done something interesting, especially. And well, any questions, any information that you feel you're lacking, feel free to discuss on the Meetup group. Let's make this a welcoming community where we all learn together.
And I'll post a link to my to my slides later on in the Meetup group.
Yeah, same here, same here. Everything will be shared. Okay. Well, thanks a lot. Thank you, Shachar. And I think we can call this a day.
Night, night.
Good night. Good night, everyone.